given that we are a bit late, and also that it is very late in Europe and it has been a very long day. So please stick around after Alexey's talk. We will immediately start the discussion session. Go ahead.
Okay, thank you very much for inviting me and so on. Can you see my screen, my slides?
Yeah, go ahead. Everything is fine.
So actually, I would like to tell some talks about some properties of doubly heavy baryons, that is lifetime and branching fractions of some weak decays. So this is the outline of my talk. After some short introduction, I will tell some words about update of the lifetime predictions, and then the case of doubly heavy baryons, Ξ+cc into Ξ+cc plus system of light mesons, namely 2 pi meson, 3, and so on. And after that, conclusion will follow. Okay, so first of all, some actually obvious words about doubly heavy baryons. In these particles can be considered actually as a laboratory to study heavy quark interaction. So they are nicely studied theoretically. We have nice theoretical prediction for masses, production modes, decays modes, and so on. And up to now, up to recently, none of these particles were observed experimentally, but approximately recently, one of them, namely doubly charged Ξ+cc baryon, was observed. It shows that it is a good agreement with theoretical prediction for mass and so on, but a pretty bad agreement for total lifetime. So what we should do, and what I will try to do in this presentation, I will try to update some parameters that were used to predict this lifetime and see how this update will change theoretical predictions. And so the other point is that since, as I have told, only one doubly heavy baryon is seen up to now, and on the other hand, B sub C meson is visible, is measured on LHCb detector. So it gives us a hope that Ξ+bc baryon could be detected too soon. So we we are interested in some predictions of some exclusive decays. So I will talk a little bit about the decays, namely this one. Okay. So let me talk something about what doubly heavy baryons are. Obviously, these are baryons that are built from two pair of the heavy quarks and the light quark. And a nice theoretical model that is used to describe these particles is quark-diquark model, where two heavy quarks form a relatively small in special terms diquark, and this diquark actually can be seen in color sense as an antiquark. So actually this doubly heavy baryon looks like a meson. So this this model gives us an opportunity to use theoretical methods developed for description of heavy quarkonia mesons to predict masses, production rates, decays, and so on. And there you can find a lot of such prediction literature in principle, especially our theoretical group in Pertino made a large number of such predictions, lifetimes also. And so, let me talk about lifetimes a little bit. So the nice theoretical model to predict lifetimes of doubly heavy baryons is operator product exchange expansion. In the framework of this model, we use the optical theorem, and so the total width is considered as an imaginary part of this effective Hamiltonian matrix element, and this effective Hamiltonian is written in this way. So as you can see, there are four fermion operators that are mixed by color interaction. And so these are Wilson coefficients with this interaction. And what can we tell about this thing? First of all, obviously for any doubly heavy baryon, one of the ways for decay is the decay of the spectator decay of a heavy quark. For example, C quark decays into S, up and down, or lepton neutrino pair. And so, okay, actually there are two other ways for decay. This is, first of all, it is Pauli interference. If there is, for example, up quark in the initial baryon, it can interfere with the up quark produced in the decay of C initial C meson, C baryon, and so these two modes, they interfere with each other, and as a result, this matrix element of this interference will be negative, so it will reduce the total width of the lifetime. On the other hand, if we do not have up quark in the baryon, but we have down quark in the baryon, as it is in Ξ+cc plus singly charged. So we have another mode, another process that is weak scatter. Okay, so the difference, it leads to nice effect that the lifetimes of two baryons, I mean doubly charged and single charge, they can differ a lot. So these are some analytical expressions for the lifetimes for matrix elements of the doubly heavy baryon that are used to predict lifetimes. For example, as you can see, if we are dealing with decay of doubly charged Ξ+cc, we have this thing. This is a matrix element of the spectator decay. This is Pauli interference. And if we consider the decay for singly charged baryon, we have also spectator decay, but also weak scattering thing. Okay, so as I have told, there were theoretical predictions for the lifetimes of the baryons, and using the parameters listed on the screen, operator exchange expansion model gave the prediction for a lifetime of doubly charged Ξ+cc baryon as about half of a picosecond. Unfortunately, after the experimental discovery of this baryon, it turns out the actual lifetime is about 2 times smaller. And so one of the ways to explain this discrepancy is to change a little bit the parameters of the model, parameters that were used in this model. And it turns out that if we increase a little bit the mass of the charm quark, we can fairly decrease the lifetime of the theoretical prediction of the lifetime of the baryon, without changing a lot the mass of the particle, and so on. So on the slide, these figures, I show the dependence of the lifetimes of different double charmed baryons on the models, on the parameters of the model. And it turns out that if we set charm quark mass to the value showed on the screen, we will receive exactly the experimentally measured value of the lifetime. So the other plot of the slide, we show also the dependence on this parameter, charm quark mass, the prediction of the width of different channels to total width of the different double charmed baryons. For example, in the case of doubly charged Ξ+cc, as you can see, with the increase of the charm quark mass, total width, and the spectator width of this baryon increases, obviously, and also the Pauli interference mass width decreases, but it is negative. And for example, if we consider the Ω+cc baryon, the figure is shown on the screen. Okay, so the same analysis can be done also for baryons that are built from bottom and charm quarks. So these are predictions dependence on the parameter on the model parameters. For example, these are predictions for width of different channels, and these are predictions of total lifetimes with the variation of different model parameters. Okay, so what we have in the result of this topic, that if we change the mass of the charm quark a little bit, the lifetimes of the baryons, they are shifted significantly, and as a result we end with the shown on the screen tables. And as you can see, there is a clear pattern that, for example, lifetime of the Wc charmed baryon is significantly larger than lifetimes of single charged baryons. This is because in this case we have Pauli interference that is negative, that decreases the total width, and obviously increases the total lifetime, and the same patterns can be also observed for other baryons. Okay, so as a result, the measurement of the lifetimes of other double heavy baryons could be very interesting for test our approach. Okay, now the second point, the second part of my talk, it will be devoted to theoretical investigation of some class of doubly heavy baryon decays, that is the case of Ξ+cc baryon, that is baryon that is built from bottom and charm quark plus light quark into the other baryon and weak boson that then transforms into some set of light bosons. Actually, in the framework of factorization model, this process is described by the Feynman diagram shown on the screen, and the corresponding amplitude can be written in this form. Obviously, this amplitude consists of three parts: some constant, then vertex that corresponds to weak decay of the baryon, and then vertex that amplitude that corresponds to adrenalization of the weak boson into final set of light mesons. The vertex of weak decay of the baryon can be fairly written in terms of form factor that are obviously non-perturbative objects and could be calculated, for example, in the framework of potential models, light front models, and so on. And the second in the physical quantity, that is the amplitude of adrenalization of weak boson, W boson, into light mesons, it is also non-perturbative, and it can be calculated, for example, in terms using the resonance model, spectral functions, and analysis of tau lepton decays. Okay, talking about the form factors, obviously these form factors can be calculated and using different models, and in our analysis we have used three models with references shown on the screen. And here, for example, I show the squared momentum dependence of four form factors for these three theoretical models. So let me briefly discuss the results. Let us first consider, for example, production of two pi mesons. That is, a W boson transforms into a pi plus pi and pi minus pi zero. Obviously, in the framework of resonance model, this amplitude can be saturated by rho meson, and the amplitude of this transition can be written in the following form. Here, the Lorentz part of this amplitude is dictated by the quantum numbers of the particles. So obviously this is vector particle, so a final pi mesons are in p waveform. So this we have the difference of momenta, and this propagator shown here, it can be written in this form. It is called photo parameterization, so it is usual propagator, but the width of the rho meson is the energy dependence of this width is taken into account. Okay, so with this nice matrix element, it is easy to calculate different distributions. For example, this is the distribution over the squared mass of the final system. So as you can see, there is a nice peak that corresponds to rho meson, and also we can build a distribution over the invariant mass of the final baryon and one of the pi mesons. Obviously, this distribution is symmetric since two pi mesons are identical in some sense. Okay, and also we can easily calculate the branching fractions. As you can see, these branching fractions are pretty large, so we have some hope to observe this decay in experiment. The only problem with this decay is that one of the final particles is neutral, and for example, LHC on LHCb detector, they do not like neutral meson. They do not. The efficiency of their detection is not very large, so it would be interesting to check the other decay where there are no neutral meson. That is decay with production of three charged pi mesons: pi plus, pi minus, pi minus. So in the resonance model, this decay can be described by the diagram shown on the screen, and the amplitude of this transition can be written in the following form. So as you can see, our initial boson transforms into A1, that then decays into rho meson and pi, and so on. So what we have here, we have propagator of A1 meson, then propagator of rho, or the excitations, and Lorentz part that is dictated by quantum numbers of participating particles. Again, the propagators of virtual resonances can be written in photo parameterization. So using this amplitude, it is again easy to construct the distributions over different kinematical variables. For example, this distribution over the invariant mass of all three particles, squared invariant mass. For example, obviously there is some hint to A1 meson, since it is pretty large. The peak is not very is large also. So here we have a distribution over squared invariant mass of the final baryon and one of the pi mesons. For some reason, there are some peaks. These peaks they do not mean that there is some resonance in these places, since there are no such resonances in the model. There is some strange interference between different channels. Okay, then we can also construct distributions over invariant masses of pairs of final pi mesons. As you can see, sorry, there is a misprint. There is okay. As you can see, there are peak corresponding to rho meson, omega, and so on. Okay, so actually we can and also, as you can see, the prediction for branching fractions of this decay is also pretty large. So we have some hope to use this decay to observe the Ξ+cc baryon in experiment. So we can expand and continue using the same method to calculate the distributions and branching fractions of decays with production of a larger number of pi mesons. For example, if we consider the production of 4 pi mesons, one of them should be neutral, obviously. Actually, there are two. There could be two ways with omega meson in the middle. Here it is shown. So as you can see, there are again the distributions. The form of the distributions, it agrees very well with what we have expected. For example, that we have pi plus pi 0 peak and so on. And there is also, so as I have told, in the case of 4 pi mesons in the final state, there are actually two, at least two different mechanisms. One with omega, A, B1 and omega, and the other one is with A1 and F0 resonances. And it turns out that with these two mechanisms, there's no interference between these two mechanisms. The reason is because in the previous case, this omega meson is very narrow. Okay, and so what do we have? I can again give some prediction for branching fractions, for distributions. As you can see, for example, if we consider distribution over squared invariant mass of the final baryon and one of the pi mesons, we also see some strange peaks in some channels. These peaks, they do not correspond to any of the real resonances, but they are visible. And again, we can see that there are some clear peaks. In this case, we know what are the resonances that correspond to these peaks. For example, here in pi minus pi 0, we know that there should be a rho meson in this channel, and with this pi plus pi minus, actually, there is F0 resonant in this channel, and there are no resonances in the channel pi minus pi nodes. Okay, so the same we could be told about decay with 5 pi meson in the final state, and in this case, again, we can live without neutral pions. Okay, so actually this is the main things of my talk. I hope I'm not too late. So the conclusion is the following. So first of all, that doubly heavy baryons are well studied theoretically, and after observation of one of these doubly heavy baryons, that is doubly charmed, Ξ+cc, a new chapter started. So experimental data give us an opportunity to update the model parameters and lifetime predictions, and we also are able to consider branching fractions and distributions of some of the decays, and such the branching fractions are shown on the screen. So the presented results were published in listed papers. Thank you very much for your attention.
Thank you very much, Alexey. So the talk is now open for questions. Please raise your hand.
Okay.
I don't see any. Oh, okay. Oleg, go ahead.
Thank you very much, Alexey, for a very interesting talk. Actually, I have a naive question. So it's known that, say, for meson production, the decay rates may be related to the just the production amplitude. By, say, if there is a decay of Chi to, say, mediated through two gluons, it's possible to relate this to the production meson from two gluons. I understand that for baryons, because of fermionic nature, it's not straightforward, but Isn't it possible to having this just OPE analysis to have some relation between decay and production?
Well, these decay, I don't think that these decays can be used to predict production. You see, then these decays, I think what you are talking about that from decay of methane into two gluons, for example. Right. Yeah. So we can obtain some information about the interaction constant of this methane.
Yeah, exactly. Yes.
But in this case, we do not need interaction. So there is no way to produce. So right now there are no, in this process there are no interaction constants that can be used in production, as far as I understand. Well, actually, I think you can use the case, for example, to consider the probability to produce these baryons from weak boson decay, for example.
Yeah.
So to consider the cross reaction of W boson into two baryons and some particles, but I think this branching fraction of this process will be tiny.
I see. Actually, you are calculating just by optical theory. You calculate inclusive, yes, decay rate.
No, right? Actually, no. So these were two almost different topics. So optical theorem was used to predict total lifetimes.
Yeah.
But these, the decays with production of light mesons, actually these were the case of, okay, I will show the screen. So these were the case, for example, Ξ+cc.
Yeah, this is exclusive, yes, yeah.
Right, this is exclusive.
Yeah.
So
but inclusive, I think for Quarkoni it's mostly inclusive. Okay, well, I see the difference. Okay, thank you. Thank you. Mm-hmm.
Thank you very much for next question.
Okay, thanks, Oleg. And